You're welcome again to my YouTube channel. Please do not forget to always subscribe so that whenever we send anything to this channel, you can benefit from it. I want to appreciate those of you who have already subscribed and those of you who are always checking on this channel. I have a reviewed question of the 2021 YF Physics Practical, which I initially posted. You will recall that I posted the question 1 of the 2021 YF Physics Practical, where I said, based on the instructions sent to schools as materials to make available for the experiment or for the exam, that I propose that the period of oscillation, that is t squared, will be varied with the inverse of the mass added to the meter rule, which we call the auxiliary mass. But going through the experiment, I discovered, just like some of you have rightly also observed, that the mass does not have significant effect on the period of oscillation. So as a result, by critical thinking, I had to look at the materials again. I know that it's very common for us to vary the period of oscillation with the length of the thread in this particular experiment, or you vary the period of oscillation with the distance between the thread while you keep the length of the thread constant. But there's a little variation to this particular experiment. And what is that variation? Is the introduction of the masses. The introduction of the masses, especially two sets of masses, and it kind of want to bring confusion. And looking at those masses, you will want to think that the masses will vary, with the period of oscillation. But by critical thinking, I discovered that no, the masses are going to be kept constant, even though we have two 10-gram mass, two 20-gram mass, and two 50-gram mass. They are going to be joined together to give us 80 grams in each side of the meter rule, and then they will be suspended by means of thread. They are not going to be placed on the meter rule, all right? They are not going to be placed on the meter rule. Look at the diagram. They are not going to be placed on the meter rule with an adhesive. Otherwise, the instruction will have said we should make adhesive like sellotape or glue available for the students. But since the instruction has not told us to do so, and we are to give the students 250 cm long thread, okay? It means that after suspending the meter rule by means of thread, they will use the remaining thread to suspend the masses. And if they are suspending the masses and they are not using adhesive, then it tells us something that the student will be required to determine the distance between the masses. The distance between the masses. They will be required to determine the distance between the masses. And to make that easy for the student is the reason why they have to suspend it with a means of a thread. So this is going to be the setup for the experiment. So don't forget, again, look at the instructional materials, 2 meter rules, 2 little stands and clamps, thread of about 250 centimeter long, stopwatch or a stop clock, a weighing balance, split cocks, and a set of masses, 2 10 grams, 2 20 grams, and 2 50 gram mass. All right, now, look at this setup very well. L is the length of the thread, D is the distance between the thread, and B is the distance between the masses. In this particular experiment, I have decided to place the thread at 10 centimeters and 90 centimeter mark. In the original question, it may not be at 10 and 90, although this is a very common position where we usually place the thread in this kind of experiment. Let's not forget, this experiment is called bifilar suspension. And bifilar suspension is an experiment that can be used to determine a lot of things. In this experiment, you can use to determine the moment of inertia of the meter rule. You can use to determine the radius of gyration. You can also use it to determine the acceleration due to gravity, of a place. So it depends on what the examiner is trying to test the student. You can even use it to determine a constant like the length of the thread while you vary other variables, or the distance between the thread, or even the distance between the masses while you vary the other variable, you change the other variables. Okay? But I am proposing that in this experiment, the length of the thread is going to be kept constant. The distance between the thread will be kept constant. But we are going to be changing the distance between the masses. All right? So look at the diagram very well. L is the length of the thread. D is the distance between the thread, and B is the distance between the masses. In this particular experiment, I have decided to place the masses at 15 centimeters and 85 centimeter mark for a start. Okay? So if the masses are placed at 15 and 85 centimeter mark for a start, the distance, which is B between the masses, will be equal to 70. And so we keep changing the masses, the distance B by 10 centimeters. All right? So this is the setup for the experiment. Now, how do you perform this experiment? Lest I forget. After this post, I will post the experiment itself, how to perform the experiment. I will perform the experiment and show you how the oscillation will look like. I will have done that today, but because my students are a bit distracting me, causing a lot of distraction in my lab as I was trying to do the recording. So I decided to suspend it and look for a more appropriate time, maybe by weekend, to do it when there will be no disturbance. So latest by Saturday this week, we perform the experiment and I will post it so that you see how it is. But this particular oscillation is such that the meter rule is going to oscillate vertically. You just twist it. You will not push it to one side. No, you just twist it through a little angular displacement, and then you allow it to go to and fro about the axis of the center of gravity. All right. Now, this is the instruction for the experiment which I have proposed. You are provided with 2 meter rules. Another necessary apparatus. Place one of the rules on a weighing balance. All right. That is going to be the function of the weighing balance that is in that instruction to determine the mass of the meter rule. So place one of the rules on a weighing balance. Read and record the mass M of the meter rule. Read and record the mass M of the meter rule. That is capital M. With the graduated face of the rule facing upwards. With the graduated face of the rule facing upwards, suspend the meter rule by 2 parallel threads of length L equals 40 centimeters, each at 10 centimeters and 90 centimeters respectively. So I've decided to use to use 40 centimeters as my L in this experiment. In the original question, L may not be 40, it can be 50, it can be 60, it can be 70. But in this experiment, my L is 40 centimeters. Read and record the value of D in meters. Take note of D in meters. And I will tell you the reason why D has to be in meters. Okay? So D is the distance between the threads, and you have to record it as in meters. Now attach a mass M 80.0 grams, each at the 15 and 85 centimeter marks, respectively. Read and record the distance B between the masses. Evaluate B square. Okay? I want to tell you why we have to evaluate B square. Why don't we just leave it as B? Why not 1 over b? Why is it b squared? All right, because some of these experiments, there are underlying formulas or principles, okay? When you try to now derive a straight line graph from such formula, it now helps you to know what and what you are plotting against each other. So set the rule into a small angular oscillation about the vertical axis through its center of gravity, and then determine the time t for 20 oscillations. Evaluate the period t as capital T and t squared. Now, keeping L, which is the length of the thread, D, which is the distance between the thread, constant throughout the experiment, repeat the procedure for other values of B when M is at 20 centimeters and 80 centimeters, 25 and 75 centimeters, 30 and 70 centimeters, 35 and 65 centimeters respectively. In each case, determine the corresponding values of b squared, t, that is time of oscillation, small t, capital T, which is period of oscillation, and capital T squared. Tabulate your readings. All right? Plot a graph with t squared on the vertical axis, b squared on the horizontal axis. Determine the slope of the graph. Now, evaluate k, where k is s over q, and where q is 16 pi squared over gd squared. All right. Now, before you can appreciate what we are trying to do in this experiment, you need to understand the underlying principles or formula that support this experiment. Now, so let's look at the background theory. The period of oscillation for a loaded bifilar oscillation is given as t squared equals to 16 pi squared lb squared over gd squared. Now, this is the reason why d has to be measured in meters, because of the acceleration due to gravity g, which is 10 meters per second squared. All right, you cannot be multiplying d squared in centimeters squared by g, okay? That would be an error. So g has to be in meters squared, all right, to be able to multiply it by g, which is acceleration to gravity. So this is the formula for the period of oscillation. T squared is equal to 16 pi squared lb squared over gd squared, where L is the length of the thread and is going to be kept constant. D is the distance between the thread, which is going to be kept constant. So the only thing that we are going to vary is B. And going by this formula, T squared is directly proportional to B squared. So if the entire 16 pi square L over GD squared is a constant, then T squared varies directly with B squared. So meaning that if we plot T squared on the vertical axis, B squared on the horizontal axis, then the slope of the graph will be equal to 16 pi square L over GD squared. So whatever you get as the slope of the graph is 16 pi square L over GD squared. All right? Now, we can also make some mathematical deduction. Let 16 pi square, remove the L, 16 pi square over GD square, remove the L, 16 pi square over GD square, let it be equal to Q. If 16 pi square over GD square is equal to Q, then T square will be equal to QLB squared. So meaning that the slope of the graph S is equal to QL. L therefore will be will be S, which is the slope, over Q. All right? Now that tells you that after you have finished plotting the graph and you have determined your slope, and then you are asked to evaluate K, where K is S over Q. That Q is the entire 16 pi square over GD square. Okay? And whatever you get will be equal to, okay, that is S over Q. Whatever you get as the value of S over Q, which is the K here, should give you L, which is the length of the thread. This explanation is just to let you know when you are correct as you perform the experiment. Because if you don't know the aim of the experiment, you will not know when you are correct or when you are missing out in the experiment or when you are doing the wrong thing in the experiment. So this background explanation is just for you to know when you are correct. So in this evaluation, if you're asked to evaluate K, where K is S over Q, this evaluation is supposed to give you the length of the thread that has been kept constant. So you'll be told what the length of the thread is, and the final result here is supposed to show us or tally with that length of the thread. Okay, so I've performed this experiment, and this is my table of observation, my composite table of observation. All right, as you can see, this is my B from 70 to 60, 50, 40, 30. Then the B squared, then the time for the oscillation. Okay, now I have already done the average here. I did not feature the first time and the second time before the average. What I have here is just the average of the time. Then the period of oscillation, which is the time of oscillation over 20, because you are going to take 20 oscillations. And then T squared. Okay? So based on this table, that don't forget that whenever you are recording your T squared, it must be recorded to at least 3 decimal places. Okay? 3 decimal places, or at least 3 significant figures. Take note. Either 3 decimal places or at least 3 significant figures. And that is the reason why you see that my B square here, because the values are large. The values are large is the reason why I decided to leave it in 1 decimal place, but have more than 3 significant figures. Okay. Now that is a B square, as T, capital T, and T square. Then don't forget the question expects you to plot T square on the vertical axis and then B square on the horizontal axis. So if you plot T square on the vertical axis and B square on the horizontal axis, the slope of the graph, you can use this table that you have here to plot a graph and follow the evaluation. You find out that your K, which is supposed to be the length of the thread, will be close to 40, if it's not exactly 40 centimeters. But don't forget something, that your B squared, based on what you have on your table, is in centimeters squared. So your slope will be having decimals up to 4. If you put it in standard form, you'll be having times 10 to the power minus 4. Okay? That is because it's in centimeters squared. All right? So all you need to do is to multiply whatever you get as your slope by divide it by 10 raised to the power minus 4. If you divide it by 10 raised to the power minus 4, it will convert it from centimeter squared to meter squared. All right? Then you can now have your final answer in in meters. Okay? Have it in meters. And the reason why you have to do that is because, don't forget, you are still going to convert your D to meter because of the G. And so it is better to convert that slope to second square per meter square than leaving it in second square per centimeter square. All right? I hope you understand what I'm talking about. So if you do that, you find out that it's usually plus or minus 10% of the actual value. So if the value, the length of the thread is 40 centimeters, 10% of 40 centimeters is 4 centimeters. So 40 minus 4 will give us 36, and 40 plus 4 will give us 44. So the range of your value, for you to be accurate, should be between 36 centimeters and 44 centimeters. So anything you get within this range, you are accurate. All right? So I am very optimistic that the experiment for question 1 on 24th of September 2021 of physics practical experiment, this question 1 is going to be on this, and you're going to have something almost exactly what I've explained. The only thing that will change is the values. Okay, the length of the thread can change, but the experiment is going to be the same. The length of the thread is going to be constant. The distance between the thread will be constant. You will only change the distance between the masses. All right. Now, these are the precautions. These are the precautions. The precautions should be stated in the right language. What is the right language? You will personalize the precaution and also make sure it is stated in past tense, because you perform the experiment, so you personalize it, and then at the time you are writing your report, you had already done the experiment, so you present it in the past tense. Example of such experiments and how it should be written are: number 1, I avoided parallax error when taking my reading on the meter rule. When taking my readings on the meter rule, I noted and corrected 0 error on the stop clock. Okay, that is if you are using a stop clock and not a stopwatch. The stopwatch is the digital one, and the stop clock is the analog. And in that analog, most of the time the pointer may not be on the 0 mark. So you have to adjust it. If it cannot be adjusted, it cannot be corrected, make sure you take note of it so that you will know how to do some plus and minus in your final value. So it also can be a precaution, especially if you are using a stop clock. And even if you are not using a stop clock and you are using a stopwatch, you can still say that you noted and corrected 0 error on the stop clock. But you'll be wrong to say you noted and corrected 0 error on the stopwatch, because the stopwatch will not have 0 error since it's digital. So I noted and corrected 0 error on the stop clock. I took repeated time of oscillation to minimize error. Okay? It took repeated readings of the time of oscillation to minimize error. That is your T1 and your T2. Usually any experiment that involves oscillation, there is a need to take a repeated time of oscillation to minimize error. So any of these 2 precautions is what you are expected to present. And then these are the short theory questions you should expect. You can expect questions such as: what is meant by inertial mass? What is meant by inertial mass? Define angular velocity. Define simple harmonic motion. Give examples of simple harmonic motion. Okay, what is inertial mass? Inertial mass is the mass of, or that property of matter that makes change in the motion or change in the velocity of an object difficult. Okay? It's a property of matter that opposes the change in motion or change in velocity of an object. Then angular velocity can be defined as the rate of change of angular displacement with time. Just similar to what you have as a velocity. Velocity is rate of change of rate of change of displacement with time. So the same way, angular velocity is the rate of change of angular displacement with time. And what is simple harmonic motion? Simple harmonic motion is the to and fro motion of an object whose acceleration is directed towards a fixed point, and it's always directed towards a fixed point, and is directly proportional to its displacement from that fixed point. All right? And then examples of simple harmonic motion, you have a simple pendulum, oscillating pendulum, you have oscillating prong of a tuning fork, a vibrating string of an instrument, and so on and so forth.